So today we're looking at LeetCode 84, largest rectangle in histogram. Problem statement is given n non-negative integers representing the histogram's bar height, where the width of each bar is 1, find the largest area of the rectangle. So they give 2, 1, 5, 6, 2, 3, and the largest rectangle is 10 here. So it's probably worth mentioning here there is a brute force and an optimal solution, and possibly other solutions here. So the brute force solution would be like loop over every possible start and end, and then loop over in a third nested loop all the bars from each possible start to end, calculating the minimum height in each of those possible ranges, and then multiply by the size of the range. That's going to be O of n cubed, I believe. And so that's most likely not the solution your interviewer is looking for. It's worth mentioning, if you're nervous, you could always start with that solution to kind of buy time. And it's probably better than completely bombing the interview and failing to come up with a solution, to at least come up with a brute force solution first, and then ask your interviewer if they want you to find the optimal solution. That way you at least have some solution to the problem and you don't look like you don't know how to code. Although I think if you're interviewing at like one of the large tech companies like Facebook or Google or Amazon, doing it in the brute force method is probably not going to look good. They're probably looking for the optimal solution. So I'm only going to cover the optimal solution here today. So let's work through this. So if we have a height map of 2, 1, 3, 4, 3, that's visually going to look like 2, 1, 3, 4, excuse my uneven bars, 3. Okay, we're going to have a few variables here. So we're going to have n number of elements. We're going to have I for an incrementer, which is going to start out at 0. We're going to have a stack, which is going to have -1 by default. We're going to have L, which is the largest we've seen. So first, we have, let me number these indexes for you. So we have 0, 1, 2, 3, and 4. And so first we are looking at I equals 0 is 2. And we need to say, is that greater than the top of the stack? Well, that's an invalid question, right? Because -1 doesn't even have a height. So we're just going to say yes, that's greater. And so we push index 0 into the stack. The stack is a stack of indexes, not a stack of heights. Okay. Now we are going to look at the next column. So I becomes 1. And we need to ask, is that greater than what's at the top of the stack? And I'll get to why we're asking this question in a second. It'll be clear, so bear with me here. The current column is not greater than what's at the top of the stack. So what that means is the previous element was a peak element, right? This is a peak and this is a peak. If we have a peak element, then including the next rectangle, rather, if we are not on a peak element, we know that including the next element, since it's larger, will always result in a larger rectangle. Okay, so we only need to check rectangle sizes when the last element was a peak. In this case, the last element was a peak. So we don't know if, we haven't seen these yet, so like let's pretend these weren't here. This was a peak, and that could have been the largest rectangle, especially if this had a height of like 7 and this was a height of 1. Okay, so because this was a peak, we need to check if that's the largest rectangle. And so to check if it's the largest rectangle, what we need to do is have a loop where we're saying, wow, the height from the top of the stack is greater than or equal to the height of the current column. We're going to run some kind of formula to check the rectangles. And that formula is going to look like Well, we need to get the height of the top of the stack. So we're going to do s.pop times I minus stack.peak. And you'll see why this is the formula in a second. Minus 1. Okay? And so we have height of 0 because this gets popped and it's 0 times I, which is 1, minus stack.peak, which is negative 1, minus 1. So this becomes plus 1 minus 1 is 1 times height of 0 is 2. So the largest rectangle we've seen thus far is 2, and that rectangle is this rectangle right here. The 2. That's where the 2 comes from. Now, we need to ask the question again. Is the top of the stack greater than or equal to the current column? Well, the top of the stack is negative 1, which doesn't even have a height, so it can't be. So we're done checking candidate rectangles. Now we need to push I into the stack. So this 1 here gets pushed into the stack, and then we increment. Okay, so we're at index 2. This one. And we need to say, is 2 greater than or equal to, is the height at index 2 greater than or equal to the height at the top of the stack, which is the height at index 1? Is the height at index 2 greater than the height at index 1? It is. We can see that visually. 3 is greater than 1 also. And so in this case, this just goes into the stack. And the reason why is because including a larger rectangle will always result, or including a larger bar will always result in a larger rectangle. And that's why we're using a strictly increasing stack, or a monotonic stack, right? As we're going up here, we're seeing larger and larger and larger. We might as well include those because we know we're going to get larger values. We don't need to like stop and check the smaller intermediate values. Okay. And this is not the height. So this is why this problem is confusing, because you're like mixing heights and indexes. So this was the index that goes into the stack too. Now we increment I, and we say, is it larger? Yes. And so 3 goes into the stack. And then we increment I again, we're at 4. Is the height at index 4 greater than the height at index 3? No. So we know the last element, or the element at the top of the stack, was a peak. We need to check candidate rectangles ending at that position. So we've got height of stack.pop times I, which is 4, minus stack.peak. Peak at the stack, it's now 2 because we just popped, minus 1. And so the height at index 3 is 4 times 1. And so that corresponds to this rectangle. And the reason we subtract 1 off of here is to exclude this bar, because we're using I as part of this calculation, which was the current bar we're considering, but now we're checking candidate rectangles ending at the previous element. So the previous element means we subtract 1 here, right? And the 4 came from where we were, and we subtract I, so we're checking from 3 to 2. We're checking just this bar here, okay? I hope that makes sense. Now we need to ask the same question again. Is the height at the top of the stack greater than or equal to the height of the current column that I is pointing to? Yes, it is, because the height at the top of the stack, which is now 2, is 3, is greater than or equal to the height pointed to by I, which is 3, because I is 4, index 4, which is a height of 3. 3 is greater than or equal to 3. So we're going to say h of stack.pop, meaning we pop this, times I, which is still 4, minus stack.peak, which is now 1 because we just popped, minus 1 for the reasons I explained. So the height at index 2 is 3, times 4 minus 1 is 2, and 3 times 2 is 6, and that corresponds to this rectangle here. And so largest gets updated. It's now 6. Now we need to ask the same question: is the height at the top of the stack, which is index 1 is 1, greater than or equal to the height of I, which is 4? The height is 3. No. 1 is not greater than or equal to 3. And so we're done checking candidate rectangles for I equals 4. We push 4 into the stack. Now we have no more elements to process, but we still have items in the stack we need to process. And so we're going to use a different formula for this. So h of stack.pop times n minus stack.peak minus 1. And so height of stack.pop, h of 4, times n minus stack.peak. Well, we just popped the 4. So stack.peak is 1 minus 1. So 5 minus 1 is 4, minus 1 is 3, times the height at 4 is 3. 3 times 3 is 6. And that corresponds to this rectangle here. Or I'm sorry, that's 9. This problem is so confusing. 9. And that corresponds to this rectangle here. Okay, so the reason we use n is because we're at the end here, and there's 5 elements, and if we're at the end, it would be like I was 5 minus stack.peak minus 1. It's the same as before, except we're just using n. It's as if we had incremented I, that's all. And the reason it's 5 in this case is because it's a zero-based array. So if we had incremented I from 4 to 5, which doesn't exist, we just get n, which is 5. So we're just using a separate formula for this just to deal with some edge cases because we can't index into the array at 5. So we're just doing a separate little loop here. Okay. And while there's still elements in the stack, we need to keep running this formula. And so h of stack.pop, and this gets popped, times 5 minus stack.peak minus 1. And so that's 6 minus 1 is 5 times the height at 1 is 5 times 1 is 5. And that rectangle is actually, let me pick a color here. We haven't used blue. That's this entire rectangle here. Okay, and now there's no more elements in the stack. And so winner, winner, chicken dinner. Largest rectangle is, well, not 6, it was 9 down here. I forgot to update that. So largest rectangle was 9. So we're going to have a stack initialized to contain -1. We're going to have n, which is h.length. And we're going to have I, which is going to be 0. And we're going to go up to n non-inclusive, I++. And we need a loop to process the remaining stack and return L. So this is the initial loop. And for the initial loop, we need to check if current call height is greater than top of stack, and if so, push, else while top of stack greater than or equal to current call height. Okay, so these are the heights, not the indexes. And so in this while loop, we're going to pop the stack, and we're going to calculate rectangle size and update L if appropriate. And when we get out of this while loop, we need to push. Okay, so if the current column height, so h of I, is greater than the top of the stack height, so h of stack.length minus 1, then we need to push, so stack.push I, else while the top of the stack is, and the height at the top of the stack is greater than or equal to the current column height, then we need to pop the stack. So because it's JavaScript, we're just going to do s.splice, s.length minus 1, 1, okay? And I'm actually going to move this here, and I'm going to calculate L equals math.max. So the largest rectangle is either the largest one we've seen, or the largest one we've seen previously, or the height of the new rectangle. And the height of the new rectangle is going to be height of stack, the last element in the stack, times I minus the previous element in the stack to that. Sorry. Minus 1. And then we need to push that onto the stack. And now we need a loop. So let's check through this, right? For our initial loop, we process through all the bars from left to right. We check if the current column's height is greater than the height at the top of the stack. If so, we push into the stack because we have an increasing element and we're using a strictly increasing or monotonic stack. So if this element is greater than the previous element in the stack, we put this new greater element in, and we keep doing that while the bars increase. And then when the bar no longer increases, or we see an element that's not greater than the top of the stack, we know the previous element was a peak. So we want to look at the top of the stack's height, which was the peak, and while it's greater than the current column's height, keep popping it off and calculating candidate rectangles. So to calculate the candidate rectangle, we look at the height at the top of the stack times the index we're at minus the previous element in the stack, minus 1. And then we update the largest rectangle, pop the element off the stack, and keep processing candidate rectangles. Then push onto the stack. And then we come out of this initial loop here, and we need to process the remaining stack. So while s.length minus 1 is not equal to -1, so while we still have elements in the stack other than the initial -1 up here, we're going to update the largest, and we're going to calculate this rectangle. So this rectangle is the height of the top of the stack times n minus s.length minus 2, the previous element in the stack minus 1, and we need to splice, because to simulate popping a stack, because this is JavaScript and it doesn't have a stack. So it's a little kludgy here, but it should work. And we need to define L up here, which is going to track the largest. I'll initialize this to -1 up here. Okay, and let's go ahead and submit that. And we need to handle an edge case apparently. So if h.length is equal to 0, we will just return 0 as expected. Run that. And that's how you solve LeetCode's largest rectangle in histogram. Thank you.